Welcome, everybody. I want to start the lecture. I want to review a few ideas from the first lecture before we go to the second one. What we discussed in the first lecture was that physics mainly has, we consider two parts. The first one is the classical physics and modern physics. And classical physics starts about from Newton. The modern physics has three branches with different models. Special relativity and general relativity, which were developed by Einstein, and quantum mechanics developed by a different group of scientists. We have seen in general what is the difference between the two regions. In both regions use the principle of relativity as one of the main symmetry principles. But they use different presentations. Representations of this symmetry is given by Galilean transformations in Newtonian dynamics, which means that the space of the background and the velocities are flat. This makes life much simpler to working in a flat space. You have parallel transport, you have addition, easy. Then when we came to solve the shortcomings that we are not able to explain by using classical physics, we had to change those transformations to Lorentz transformation. And Lorentz transformation already put you a restriction on the velocities. So we are now talking not a flat space, there's a boundary on a bounded domain of possible velocities. And things became more complicated. And also in general relativity, we had to put a metric non-trivial on the space because of the fields. So we have to change the model. But in all cases, we want to have the Newtonian limit for each theory, because Newtonian theory works very nicely in general. So in order to check that a theory is valid, you have to be always able to show that in the right limit, it gives you the Newtonian approximation. Now, even the way I will present you, this limit will be even stronger than it is used in other theories. You see that you don't need very big change to make due to the theory to make the theory passing all the tests that relativity is was passed till now. So therefore, today we'll spend our time to teach all the parts from classical mechanics that we will need for the next lectures. This is the second lecture, and today the topic is classical mechanics. When we talk about physical processes, you have to have a way how to describe them. We'll talk mainly in these lectures about dynamics. Dynamics, that's motion of objects. So to describe motion of objects, they have to be, the motion has to be with respect to some space and time. So we start what we call the frame of reference. To be able to describe something mathematically, you need numbers. And you start axis, x, y, z, to describe, you have to choose the axis to be able to label any point in space by three numbers, x, y, z. And you need a clock to be able to measure the time of an event. Since we are talking dynamics, so things are changing, you need both of them together, because otherwise you don't know if something moves, what is its position without telling me at what time. So that will be the frame of reference, will be if we choose the axis and we choose the clock, and we have to be able to measure the time at any position in space, then we know how to turn any event into a into 4 numbers. Then we want to understand what is, which reference frame is an inertial. For this, we need to have few devices. You need an accelerometer, which is measuring the acceleration of a rest object in your place. It's a heavy ball. It has sensors around him on the walls. So the way he presses on each of those sensors, you understand what is the gravitation or the acceleration felt in this system. There is another device you have to understand if you are not rotating. For this, you have a gyroscope. This is a mechanical gyroscope where you see on the picture. But this one is more interesting. That's a fiber optic gyroscope, which is currently used. And one of the lectures, I think 2 from now, I'll explain you how it works, because it is a very interesting device and really expressing very relativistic effects. Even though there are people trying to explain it classically, it is wrong explanation. It's a purely relativistic effect, and we'll discuss it later. After you have those devices, and we can say what is inertial frame. You cannot have ideal inertial frames. It's very difficult, but we can get it locally inertial frame. That means almost ideal. And for instance, that's a picture of a space station. The astronaut is in the air, sitting in the, all the things are in the air because there's no acceleration. If you would have an accelerometer, it would show you 0 acceleration. And if it's not rotating, everything stays on the place. That means it is almost an inertial frame. It's not perfect. If you leave it for a long time, it will drift a little bit. There's another in Bremen. There's a drop tower. In the institution, I work with them now on an experiment. In this drop tower, they have a lab falling from the top down. And inside this tower, there is no air, it's vacuum, very deep vacuum. So it falls with free fall. In the free fall, you have an inertial system, almost perfect inertial system. So if you need to have experiments that need inertial system, you can use it here, but not for a long time. It has about 1 minute, 2 minutes for the whole experiment, so we have to do it fast. And this satellite, any satellite, it comes on the orbit and goes around. If you don't apply the engines, so it's an inertial frame, local inertial frame. Now we have to, in order to describe physics, we have to talk about also space-time transformations. What is this? So space-time transformations, you need to tell me, we have to understand what happens when we transform events from one inertial frame into another. If we observe some kind motion, we give it as a sequence of events, and those events, I describe the law in my frame, and somebody else described it picked up its axis differently and measures the time differently, but we have to both measure the same, using the same measuring sticks, both, for instance, measuring in meters, but we are maybe dynamic with respect to each other. So we have to understand how I am translating the sequence of events from my system to the sequence of events in this system. That's what's called space-time transformation between inertial frame. That means you have to have a map and a system denoted tag, that's not derivative. It's tag, t tag, x tag, y tag, z tag. There's the 4 numbers that were measured in system K prime. And the other system measured t, x, y, and z. And I have to have a way how to build up from those one, this t, x, y, z. Because then I can use what is called a very important principle physics, principle of relativity, which states that the law of physics are the same in all inertial frames. Even don't need the inertial frame, it's enough to ask two frames moving with constant speed with one to other, with respect one to other. For instance, your lab frame on the Earth and an airplane moving with constant velocity, any experiment in both places will look the same. So this principle gives you the information about L. First of all, it tells you there is no preferred inertial frame. In each inertial frame, the laws are the same. So if you have two frames, you cannot say one is at rest, the other one is moving. You can say the opposite. The transformation, on what it can depend. It can depend only on the relative motion between the frames. So you need to find how you identify the transformation L if you know the relative motion between the frames, which means the velocity of one frame with respect to other. Now we have Newton's first law to understand this transformation. Newton's first law tells you in an inertial frame, an object moves with a constant velocity unless acted upon by a force. This is called uniform motion. It is described by a straight walled line. Walled line is simply the graph of your motion. So you have one coordinate is t, and then you have the x, y, z coordinates at time t. It means we will consider the graph, which will be a line in the four-dimensional space, which we call space-time. So only in space-time you have a geometric description for uniform motion, because the trajectory in the space itself, it is by a straight line, doesn't mean it's uniform. It can be free-falling stone, gives also a straight line, but the velocity is changing. So in order to understand the geometry will be connected with the notion free motion in a uniform system, you have to use 4 dimensions. Since uniform motion in one inertial frame is also uniform in the second frame, that means, and we said uniform motion is connected with free motion. So something is free in one, is free in the other one. So the space-time transformation preserves lines. If they preserve lines, such transformations are called affine. The collection of such affine transformations form a group which is called the Poincare group. We will not deal with this group. We'll add an additional assumption. We need a subgroup of it. It is if the frame had common origins, spatial origins at time t and t prime was 0. That means the four-dimensional 0 vector is the same. So the transformations are linear. If you have an affine transformation, it's always a constant vector plus a linear one. And if this additional condition that we put on, that this constant term doesn't exist, so we're talking about linear transformation. And this follows directly from Newton's first law. Now we want to describe, we have two systems, picked up two systems, x, y, z, system k, k prime, x prime, y prime, z prime, and which k prime moves with velocity v between the systems. We want to define Galilean transformation, which is known the L transforming. You had an event here, you measured it in system K prime, and I want to know how it will look. We measure it in system K. As I said, the transformation is linear. Linearity follows because we assume 0, at the time 0, the two origins were at the same point, and therefore it's a linear map. The problem has a symmetry. We have motion in two directions. So there's no preferred frame. So you can say both frames move in this way with respect to others. So right and left is the same. So it cannot be that, for instance, y and y prime will not be the same. From the symmetry, it follows that y and y prime are the same. Those two, and z and z prime are the same. On the x you cannot say, because in the x you have the action of the velocity. So the velocity changes the position in x. So you'll have some matrix. You'll need that here you have the identity matrix. You must have zeros here because they cannot give ingredients into Z. And you'll have a matrix A, B, C, D. Now, this is true based only on the principle of relativity and this Newton's law, which is assumed in any theory. So from here on, we go to the assumption of Galilei. Galilei's assumption was that the time in both systems is measured in the same way. That means t must be equal to t prime. And generally, t is equal to at prime plus bx prime. So a must be 1 and b must be 0. Now, the next thing we will get is following. If you look what happens with the origin of system k prime, that means origin of system k prime, we have to put x prime equals 0. What we will get? And y prime, z prime, 0. So you'll get the x will become ct prime, ct prime. This tells you that this origin moves according with a constant velocity, with velocity c. So c is the relative velocity between the system, c is this, and x prime, that the coefficient is 1, it follows once more. You have to do a little more carefully the symmetry, checking that the transformation in one direction and the inverse one has to be similar. So you get that also x, the coefficient of d, must be 1. So we came what is called Lorentz transformation. So now we will use notation that's used in physics for describing vectors. Vectors are described by bold letters. To save time and make the formula shorter. By the way, we'll see that Einstein introduces a lot of good notations that makes notations much shorter, but we will discuss it next time. Now in classical mechanics, R will denote the position of the object x, y, z. It's bold, that means all the three numbers, R prime and this. EV, the relative velocity between the frames. So the transformation, even you don't need even assume v is in direction of x. In general, you'll get t equals t prime, and r is equal to vt prime plus r prime. That's the generalization of the transformations we said now in the previous slide. Now, if we want to understand what is velocity transformation. This has to be thought out more carefully because the definition is sometimes misleading. What is the real definition? You start with an object, it moves with velocity u at some time at k prime. Maybe for the beginning, let's start with constant velocity. That means, for instance, example r prime equal u prime times t prime. That's what it means. The position equals the velocity times the time. Now we want to understand what it is velocity in frame k. What we have to do, we have to transform this vector by this transformation. Here it's written. R has to be equal vt prime, and r prime, we substitute this one. We can take out t prime, and we get v plus u prime, and using the t is equal to t prime equals t. That means that in my system K, R is equal to V plus U prime times T. So that's what is called velocity addition. It's really not addition because the role of V and U prime are not the same. V is the relative velocity of system K prime. U is the velocity within K prime. And the sum represents how I see in system K my velocity. This is very simplified form of velocity addition. The velocity of object in K is u, which is equal v plus v prime, and that's called the velocity addition. Now how we define acceleration transformation. So if the velocity u prime varies in time, the acceleration is its time derivative of the velocity denoted by the derivative we put a dot above the vector. Dot above the vector is the derivative. The primes are here not derivatives, it's primes. So differentiation in all our today things will be with respect to time, and it's denoted by dot about the object which is differentiated. So if we look on this formula, we have u of t equals v, maybe v is constant, that's the relative motion between the systems, and u prime is depending on t. And when you differentiate them, you'll get a of t, v will get 0, and a prime will be a prime of t. That means the acceleration in any two inertial frames is the same. That's a big difference. The velocity changes, the position changes, but acceleration is the same. So we want to have a theory which should be invariant under the Galilean transformation. It should be depending on A. And that's really what happens. Newton's law of motion. The first law we already mentioned is a different formulation of it in an inertial frame of reference. An object either remains at rest or continues to move with constant velocity unless acted upon by a force. Second law, in an inertial frame of references, the vector sum of the forces an object, sum of forces. Really, in classical mechanics, the sum of forces, that's what causing, is equal to the mass of the object multiplied by the acceleration of A of the object. That is the main equation that we will use today, and all its consequences we try to understand. That's the main law. F of R, assumption is the force depends on the position, equals m r double dot. That means it's a second order differential equation with respect to the unknown function r of t, and that's what physics has to solve. There's a third law. The third law tells in an inertial frame of reference when one object exerts force, simultaneously exerts a force equal of magnitude and opposite in direction. We have always that you act on something, the other object acts on you in the same magnitude and in the opposite direction. We'll also use this law, less time, but it will be also important. Those laws are invariant of the Galilean transformation, while if you move to another system, the vector f is assumed to be f of r will be now the same f at the new point r prime, and r double prime is the same as r prime. So the Newton's law are the ones which are invariant on the Galilean. Now we'll start to go examples. The first example, which almost happens in most cases in physics, is the harmonic oscillator. Very important example. This is the example uses as the first approximation for any motion which is is limited in space and has some kind of periodicity happening in all the places around. And the simplest case is one-dimensional. You have a string connected to something that can move on the table. The force, the assumption is minus k times x. X is the displacement from the point where the free point, when the spring is free, to the point where it is after it's stretched. And the force, as you stretch it more, gives you became larger. It's proportional to this change. the direction is in opposite to the change of x, therefore we have a minus. And k is the coefficient of the spring. Second Newton's law will be mx double dot, it's the m acceleration equals the force. This is a type second order differential equation which teaches in any course of differential equations. Characteristic equation you have to solve with lambda square equals minus k over m. That lambda is square root of k over m times I, so you have complex solutions. For the characteristic equation, the general solution is c times cosine omega times t, or sine omega t, which by using some trigonometry, you can write it as an amplitude, and cosine omega t minus phi naught. That's the solution for a harmonic oscillator. And from this thing, you have to understand that the frequency, as the spring is larger, the frequency becomes larger. As the mass gets larger, the frequency goes down. And it is independent of the initial condition. That's why very interesting that the frequency depends only on the properties of the system, the coefficient of the spring and the mass of the vibrating object. Next example, uniform rotation. If you have a massive object and connected by a wire and you rotate it, and assume that we want to understand what are the forces here. So in this case, I prefer to work, you can use polar coordinates, but I prefer to work with complex representation of the plane, because this provides you additional tools for calculating derivative, acceleration, and you see it makes all the calculations simple. So introduce complex numbers by the point xy in the plane will be assigned a complex number x plus iy. And we will use complex number, you have the polar decomposition, z of t at a point t, so r is depending on the time t, and no, we are talking about circular motion, so r is constant, and angular velocity is defined in such a way that the angle changes omega times t. Omega is measured in unit 1 over radian. Now, if we want to find the velocity, we have to differentiate this. R is constant, so you differentiate the exponent, you get I omega R e power I omega t. You know that the magnitude of this is I times e power I omega t is a vector which is perpendicular to the vector e power I omega t. Multiplication by I changes by 90 degrees. So, and that's the magnitude omega r. So the size of the velocity is omega r, and it is perpendicular to the vector z of t. The second derivative, that means that the acceleration is given by a small differentiate omega and r are fixed. You differentiate in power I omega t, you get a minus omega square r. That means the acceleration will go in the same direction, in the radial direction, but not outside towards the center. And the size of the acceleration is omega r. And if you use the value of this, it's v square over r. So you know the velocity, you know the acceleration. For instance, you can tell us what is the force that the object will pull the wire. It's called the centripetal force. It's mass times the acceleration by second Newton's law, which is m omega r, or if you use the second formula, mv square over r. That means as your velocity, for instance, increases twice, the force increases 4 times at the square of your velocity. And as the radius is larger, the force is also getting larger. And the same thing about omega is quadratic. Now we go to few laws which are called conservation laws. Very important laws because it is not so easy to solve except those simple cases where we are able to understand what the solutions are. Generally, you cannot solve directly Newton's second law. What you do, you use conservations, and then this gives you a simplified equations that you're able to solve. For instance, let's go to the first conservation, a very important conservation law called conservation of energy. It holds in general case, no, as one assumption, only for conservative forces. What is conservative force? A force is conservative if the work done along a work is an integral of the force times dx, along moving an object between 2 points is independent on the path taken. That means this integral will not depend how you reach from one point to the other. This is equivalent if you do a circle path, the work will be zero. That you need to gain and to reach to one point, that you will lose the same work coming back. And there's a mathematical theorem. If the force is conservative, there exists a function u of x called the potential. And really, u of x is simply this integral from a given point to the point x, such that, in this case, the force equals the gradient, negative of gradient of u. Really, the minus is a convention. But you could use u, define it with the opposite sign, then it's also okay. On the trajectory x, we denoted x of t. X dot means the x dt, as I said, and x double dot is the acceleration. And the second law is mx double dot equals minus gradient u, because we assume that f is minus gradient u. To get the conservation, you need the following thing. You have to bring those two things on one side and take the dot product with the velocity. X dot is the velocity. And then to recognize that this equation, which is written here, is simply the derivative of such expression. Why? When we differentiating by t x dot square is the scalar product x dot with x dot. When you differentiate one side, you get x double dot x dot, and then you have the plus differentiation on the other side, which is the same for symmetry of the dot product, and this will cancel the 2, and you'll get mx double dot x. And when you differentiate u is a function of x, y, z. You differentiate by each one of them, and then you differentiate du dx, dx dt, plus du dy, dy dt. This way, what you'll get, it is gradient of u dot product with x dot. So exactly you see the equation here. This equation is the same as this. But what does this mean? That on the trajectory, the derivative is 0. That means the expression here is constant. And that's what we call energy. It means the expression mx dot square over 2 plus b is constant, denoted by e, is the constant on the trajectory. It means on any trajectory, a solution of the differential equation, of the evolution equation, you'll have a conservation. This part you have to understand, the two parts are very different. This part depends only on the mass of the moving object and its velocity. It doesn't depend on the field, on the force, while this u is independent on the object. It depends only on the position and the force at this position. So there's a split of the energy into two ingredients, kinetic. The first one is kinetic, and the other one is potential. Okay, unfortunately, this splitting is only classical. And really, when we get to the modern one, we lose this splitting. But it is approximately true as of that. We need another conservation law, which is called conservation of angular momentum. Conservation of angular momentum holds only for a central force. A central force is a force which has the radial direction. It means you have a center for this force, like this is the center, and this is R, and it's in the same direction, in the radial direction. So you can write it as a function. When I write not bold R, that means it's depending on the length. The length of the vector is a scalar, and therefore it's denoted without being bold. And that's the definition. And R hat is a unit vector in the radial direction. Second Newton's law for a such thing tells you the following: m r double dot equal the force, which is F r hat. Now, what we can do now, we can take this equation and multiply vector with the vector product with r, both sides. Now, the right-hand side, this part, we have r hat and r are in the same direction. Vector product of two vectors which are collinear in the same direction is 0. So therefore, you got r double dot cross r is also 0. But this expression, I claim, is the derivative of such expression. Why? When you differentiate this, you get two components. You get mr dot, which is written here. And the second one, will differentiate this term, you get mr cross product with r double dot. This is 0 because you have r dot cross with r dot, the same vector. And this is because we have seen here, r double dot cross r is 0. So you need to have the same way as we had earlier, that this expression, mr cross r dot, is conserved. Angular momentum is defined mr cross r dot is conserved during the motion. For instance, one of the consequences, in the motion, you can, at the initial condition, initial state, you have your object at some position r, and the velocity in another one. You can draw a plane through the initial vector r and its velocity. The angular momentum will be perpendicular as a cross product. And since it's constant, so all the motion must remain in this plane. That means if you have a center of force, your motion is only in 2 dimensions. The 2 dimensions is the plane generated by the initial radial vector, initial velocity. So you have a nice conservation law, and it reduces your problems in the central field, central force, to equations in the plane, and then you'll be able to use complex numbers, and this makes the problem solvable. Okay, now I want to discuss with you, since we'll talk about fields acting at distance, and we have 2 fields in classical theory which act at distance. There's gravitational field. The sources of such fields will describe how this field, what is its magnitude, how it acts between 2 objects. One of them we'll call the source, and the other one we'll call the object. Both, in order to generate a gravitational field, they have to be massive objects. The force equals negative mg is a gravitational constant. M is the mass of the source. M is the mass of the object. Divided by the r squared is the distance from between the source and the object. R hat is the direction, the radial distance, direction as we had earlier. Minus tells you that it is attracting. The gravitational force always attracts the object toward the source. If you look on the electric field, you have also the sources. Both of them have to be charges. And the force is almost the same. It is F equals K, same kind constant for units to connect the things the right way. You can make it also 1 by choosing the right units for the charges. Q is the charge, capital Q is the charge of the source, small q is the charge of the object, and r is the distance, r hat is the unit vector. Here we didn't put a minus, one small convention, the way how you choose the q's. So we see both look very similar, and there's a symmetry between the source and the object. You can replace the object and the source, and the formula will be the same. It's the product of the capital M and small m, and here's capital Q with small q. So this is some kind of expression like the third Newton's law, that the action of the source on the object is the same force the object acts on the source. So it looks like they're very similar, but there are differences. And the differences should be understood better, but let's see what they are. First of all, the masses that occur here, they're always positive. That means the gravitational force is always attractive. While the charges, we have positive and negative. So charges may attract and may repulse. That means that's one difference. Maybe we'll have some kind of ideas from the next lectures what is the source for such a difference. What is interesting for the gravitational field, if you put in now second Newton's law, F equals ma. Since we see here also the m, the mass of the object, the m will cancel out, and you'll get A equals gm of r squared r hat. That means the acceleration generated by gravitational field is the same for all objects. Doesn't depend on the object. Even more so, it acts in the same way even for objects with zero mass, which is not defined. There are objects with zero mass like photons, and the formula is true also there. But it has to be defined properly. Now, on the other hand, here, if you put ma, it doesn't cancel because this force depends not on the masses, it depends on the charges. So we'll have a term Q over m, which depends on the properties of the object. So this depends on the source, but this one depends on the object. So that's another difference. For gravitational field, acts the same way on all other objects. For electric field, it depends on one parameter, Q over m. Okay, from now to the end of the lecture, we'll solve two major problems, the one body and the two body problem. The first one is called motion of planets, or one body problem. It starts as follows. You have a central force, and you know the potential exactly coming from the gravitational potential. We need the gravitational force. When you integrate, the force was gm, capital M, small m over r squared, and the integral gives you 1 divided by r. So you have a central force, and you have a planet m, we'll call the mass of the sun, which is put in the center of the axis. Small m is the mass of the planet that's moving around. As I said, the answer has to be independent on M because the gravitational field acts on all objects the same way. To describe this motion, we will use the plane of motion, will complexify the plane of motion. Why there's a plane? Because we said angular momentum conservation tells you that your motion is a plane. So you can pick up complex plane, as we have done x plus I y, call it capital R of t, and we decompose the polar decomposition, R of t now, it depends on t now, and e power I phi t. Really, to describe the motion of a planet, we have to give us the two functions. How far it is positioned from the sun, and what is the angle from a given, pick up one of the stars with respect to this star. So you have to be given, to tell us what are the functions R of t and phi of t. And you want to derive them from Newton's laws. So here's how you solve it. We will need the formula for its velocity. We differentiate this. When you differentiate first the R, we get R dot, just will depend on t, times e in power phi t, and then you R is left, and you differentiate e in power I phi t, you get phi dot times I, e in power I phi t. We will need also to know we'll use energy conservation, and energy conservation has the velocity square. R dot is the velocity. What is the size of such a vector? Now, e in power I phi is of length 1. So this part has length R dot. Here, I times e in power phi is also of length 1 and perpendicular to this one. So by Pythagorean theorem, R square is equals R dot square plus R square phi dot square. So we have an explicit form for the magnitude of its velocity. Angular momentum conservation. For this, I have to calculate. We'll use per unit mass. That means m we took 1. The mass is constant, so also without the mass it's conserved. So I take this r, which is written here, and take cross product with this. What will happen? This term cross this one is 0 because both are in the same direction, e in power I phi t. And this with the second term is perpendicular. The cross product of two perpendiculars is the product of their sizes. This has the size r of t, this has r of t also, and phi dot. We have r square phi dot. And that's equal what's called J. That's how they denoted the angular momentum per unit mass. So we got now a nice formula for phi dot. Phi dot is related from here, J over R squared. That's the second formula that we will need later. Now we want to use the energy conservation from this, we will be able to derive the trajectory of a planet. Here's the energy, regular formula, mr dot, which is the v square over 2 plus u equals e. It is always better to work with unit-free things in physics. Why it is important? If we want to use, especially for us, if we want to use nonlinear things, we cannot work with quantities as units. If you have something in units, let's say meters, then to take some function of it, that means expanding this into a power series, so you have to add the square of something, it should be meter square, and meter square cannot be added. So you'll not be able to do nothing except linear transformation, linear function. But if you have dimensionless things, you can't do anything because then any function is well defined. So we turn these equations into a unit-free equation. That means you have to divide by some energy to get it unit-free. There is an energy which is, you would like also to have some kind of control. After you divide, you get unit-free things. You would like that they will be less than 1. That you'll be able to expand them in a power series. You know that they're less than 1, and they're convergent set. So what we do, we divide by this expression, mc squared over 2. You know the velocity is always limited from relativity, but you don't need it. You can use it also in classical way. A unique velocity c, the velocity of speed of light. So you divide by mc squared over 2. The first term became, you divide m by m and 2, so they cancel to get r dot square over c squared. That's the first term. What will get the second term? You get u over the 2u and r dot square, and that we write in the following. Okay? The coefficients will be u was written here. You divide it by m, it cancels. You got c squared in the denominator and the 2 on the top, and call this constant rs. It's Schwarzschild. It has a name. It's Schwarzschild radius. And u is the ratio between the Schwarzschild radius and the distance, the radial distance. The Schwarzschild radius is very important radius. It is such a radius that if you are at this point, in order to escape the gravitational field, it means the strength of the gravitational field escaping, that means you have enough kinetic energy to run away. It has to be larger than u to escape. So in order to escape, you'll need the speed of light. And if you know that they cannot have velocities above the speed of light, that's always this term rs over r. In a realistic region, it's always less than 1. And you'll be able to use power series expansion about this number. Generally, it's very small. What we do now to obtain the equation for motion, we substitute into this equation the value. Here r is bold. R squared, we use this one. So here r is already the radial distance velocity over c squared. This term gives us, using for phi dot square j squared over r squared, r in power 4 will get j squared over r squared here, and c squared from here, minus u of r equals equal. This is the equation that gives us the trajectories for motion of planet. Now we continue how we solve it. It's still not so simple equation. It's a differential equation, first order, but nonlinear. You have this term r squared in the denominator. U of r has r in the denominator. So you need to work a little bit to be able to solve. So that's the equation. You want to solve this equation. I repeated it here. And the idea is solve it not for r, solve it for u, for this dimensionless potential energy, which was r s over r. And also solve it not for the variable t, for the angle phi. It means you want to define how the potential energy changes with the angle on the trajectory. And if you know the potential energy, how it changes, you know how r changes, and you know the connection phi dot, how it's respected with r, you'll be able to find the timing also. So that's the whole idea. It will turn out that for this function, the differential equation is very simple. That any student that took a differential equation course knows to solve it. So we want to do the substitution. So we have to now to learn how to differentiate it. And we know the derivative of u with respect to phi u prime. And we differentiate as function of a function. Rs over r is the derivative rs minus rs over r squared. the derivative, the r d phi. And then we use the derivative, the r d phi can be written r dot over phi dot. Because we differentiate the r dot is the r dt, and divide by the phi dt, you get the r d phi. Now phi dot, we know what it is. It's j over r squared. We substitute it, and we get that u prime is equal to rs over j minus, which is a constant, times r dot. So the expression which is written here is really a multiple of u prime. And now, we can substitute now, and what we will get? This term squared for r prime and c squared. This is the first term, u prime squared. Now this term, to be able to get u is rs over r, so you multiply by rs squared and divide, and this is the same coefficient, you get u squared. And this term is u. Now, you can, to solve such equation, the only problem with it is that you have a square, and there's a standard trick how to get from the square linear equation. You differentiate it. You differentiate by t. Now you recognize, very important, that the two coefficients are the same here. So you can multiply by the inverse to make them 1 and put them on u. What you'll get? Differentiate u dot square, you'll get 2u dot u double prime. Differentiation is by phi. And for u square, you'll get 2u u prime. U we took on the other side to get u prime. And this coefficient moved on the other side. Getting this. Now you can cancel u prime, and divide by 2, and you get the following equation. U double prime plus u equals mu. And mu is this constant. Okay, we got a differential equation. Now it's a differential equation everybody knows to solve. It's a constant coefficient, second order differential equation. We solve it, the homogeneous one, which is the same as we solved for the harmonic oscillator. But here is the coefficient omega is 1. Because we have this near u, we have the same coefficient as u prime. And here is 1. And the non-homogeneous solution, u equals mu is a solution, because if u is equal to mu, u double prime is 0, it's a solution. So the general solution is mu plus the solution of the homogeneous equation. You can take mu outside, use trigonometry to bring it to one function. We have very, very nice formula. The formula tells you the following. On any such trajectory, the potential energy makes regular oscillations as harmonic oscillations, cosine, with respect to some value mu. What is the value of mu? It has very simple meaning, because the integral of this cosine will be 0. So this is exactly the average value of the potential energy. And what is epsilon? If epsilon is 0, you'll get u, which is connected to r, will be constant. Means you get a circular orbit. As epsilon grows, you get more eccentric orbit, more elliptic. So you return to r of phi. From here, from the definition, r of phi is rs over this u. And you get this formula, rs over mu times 1 plus epsilon cosine minus phi naught. Phi naught is the direction of the axis of the ellipse. Ellipse in polar coordinates. That's the definition, what ellipse looks in polar coordinates when the center of the axis is chosen as one of the foci. Mu is the average dimensionless potential energy, and the centricity is epsilon. So we solve the problem. Now we know how to find out one of the major conclusions of Newton's theory was that the motion of planets are by ellipses. And we know even what are the parameters. You can see what is the maximum value and epsilon cosine can be +1 and -1. And it's +1, the denominator is largest than r is the smallest, that's called the perigee. When it's -1, it's called the apogee, is the furthest distance. And we know that it repeats in each period itself because we have cosine phi. Adding 2 pi, you came to the same distance. So the ellipse repeats itself, and that's exactly the solution, the classical solution for planetary motion. Do you have questions? If not, we'll go to the next model. Next one is related with the two-body problem. Really, in most cases, we don't have, the first problem ignores that the second object acts on the source. And generally, each one acts on each other. So really, one of the major problems to solve in physics is the two-body problem. You have two objects acting one on the other with a force in the one in the direction of the other. And that's here what it helps to solve this problem, the notion of center of mass. You have two objects of mass m1 and m2 at the positions r1 is here, r2 is here, and position vector respectively. We define the relative position vector r2 minus r1, the displacement between the two masses, between the two objects. R hat is the unit vector in the direction of r. And our assumption is that the force acting on object 1 is by given Fr times R hat. Maybe I probably had to put minus. Okay, it works also. F can be negative or positive. By Newton's third law, object 1 acts on object 2, and his force is the negative of the force of F. Now, let's use this. Newton's second law tells you mr double prime, r1 double prime is equal to F, because the first object is acted by a force F. The other one is acted by a force F minus 1, so m2 r double prime is F, and F minus F is 0. This implies that we have a notion of center of mass. We took mr1 to some r double m2 r2 divided by some constant to become a point on this line connecting between them. What is the second derivative of it? The numerator is constant, so it remains. The second derivative of the numerator is exactly what it's about, which is 0. What it means, the second derivative of r is 0 with respect to time. It moves with constant velocity. So what we do, we pick up, we'll solve the problem in an inertial frame with the center at the point r. So we have to move to the system with the center of mass, and there we'll solve the problem. But it turns out that the problem becomes very, let's look what will be in K, what is the position of object 1, denoted R1 prime. It's R minus capital R. Substitute what is capital R. Capital R was M1, M2 divided, M1 R1 plus M2 R2 divided by the sum. You substitute this in this formula, and make common denominator, and you'll get this formula. You'll get that in the new coordinates, R1 prime is connected to R with a constant, which is, and the same thing for R2 prime, also defined by R by another constant. So that means we can know the trajectory of R prime and R2 prime if we know how R changes with time. It means instead of talking about 4 points, now we have only one function r. Thus, it's enough to find only r of t to solve the two-body problem. Acceleration, second Newton's law. We can rewrite it in the following way. We divide by m1. This is even a better way to find the second Newton's law, because really what we want to find in the Newton's law, what is the acceleration, not what is the force. The force is given. And so r double 1 double prime is 1 over mf. R double 2 double dot is minus 1 over f, because that's its force. And for r, which is the difference of them, r1 minus r2, what we'll get, minus will cancel with this, we'll get minus 1 over m1 plus 1 over m2f. That means we have now a similar formula as here for r1 and 2. If this would be 1 over something, some mass, then it will be exactly the second Newton's law for one variable r double prime. And this is the evolution equation, second Newton's law. For an object of mass, this rho is simply 1 over this expression. You take the common denominator, m1 and 2 goes on the top, and here we get m1 plus m. In a central field, f is central with respect to it. So now let's look how the solution goes now. So we'll see how to solve the problem, what is called a binary star. A binary star is a pair of stars removed far from all other stars. So what those stars, let's assume they have masses m1 and 2. The gravity force, that's the general force between two masses, is g m1 and 2 of r squared. But look, this expression can be rewritten in the form g capital M rho of r squared, where m is this expression. M times rho gives you m1 and 2, because m plus m2 cancels with this one. So the two formulas are the same. So the force can be rewritten as a motion of the force in even the source is capital M acting on rho. That means it's a motion of a planet of mass rho in a sun of mass m1 plus m. Now that's exactly the problem that we solved a few slides ago. And we know what is the trajectory of the planet and the gravity of a sun of mass capital M, of a planet of mass rho. And this is the ellipse. So we know that's the full picture. So we solve this for r, we get this ellipse, dashed ellipse. The dashed ellipse is simply helping us to get the real solution. Gives you the equation r of t. But we have explicit formulas for r1 of t, which is negative times 1 coefficient. So it moves in this way by this ellipse. And the other one moves by the second ellipse. So two such stars move by ellipses. Those ellipses are defined exactly from the formula that we get from the planetary motion. And it gives you full solution. So here we sometimes in astronomy there are stars which are called pulsars, which is very easy to identify since they're sending pulses all the time and with a certain very definite frequency, so you can easily identify them. And from the motion of them, you can identify what is the other one, because you don't see there nothing moving around. And goodbye.
Thank you.
Okay, bye. Thank you, Yakov.
Thank you.
Thank you.
Bye.
Have a nice day.